By now, you should be familiar with the derivatives for sine and cosine. I added a trig identity handout to the VLE to help you remember your trig identities from functions. In this lesson that we're going to do today, you're going to explore how to take the derivatives of other trig functions by relating them to sine and cosine and then simplifying them using our known identities. We're going to be using things like our regular quotient identities, the reciprocal identities, the Pythagorean identities. So if you are not familiar with those, I did go ahead and post this handout to the VLE. Now would be a really good time for you to pause this video and go back and take a look at that, because we are going to lean heavily into these to be able to take the derivative of some of our other trig identities like tan, secant, cosecant, things like that. So let's start by looking at the derivative of y equals tan x. And we're going to tackle this by writing it in terms of sine and cosine, and then using our regular derivative quotient rule to find the derivative. So when we do that, at the end, we want to simplify our answers by writing it in terms of the fewest number of functions possible. And that's where your trig identity handout is going to come in, with a denominator of 1 and no negative exponents. So remembering back to functions, we hopefully remember that if I have sine of x over cosine of x, that actually is equal to tan of x. So that's what we're going to use here. So we know that tan of x is equal to sine x over cosine x. So that would mean that in this case, y is equal to sine x over cosine x. So now we can use our quotient rule. Remember, we have derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. So we are going to use our quotient rule, which tells me that my derivative will be derivative of the top times the bottom minus top times derivative of the bottom, all over the bottom squared. So we know that our derivative of sine is going to be cosine of x. So we will have derivative of the top, which is cosine x, times the bottom, which is also cos x, minus the top, sine x, times the derivative of the bottom, which is negative sine x, all over our bottom squared, so cos squared x. So now we're going to simplify this. So cos x times cos x becomes cos squared x, and sine x times negative sine x, so negative sine x times negative sine x, becomes positive sine squared over x, and the bottom stays the same. So now we're going to use our trig identities, our Pythagorean trig identities, to figure out what is happening here. And if you remember, if you don't have the handout right there in front of you, our Pythagorean identities, are going to be sine squared theta plus cos squared theta equals 1. Secant squared theta minus tan squared theta is also equal to 1. And cosecant squared theta minus cotan squared theta is equal to 1. So what we're looking to do here is to figure out which one of these works. Well, we have cos squared x plus sine x squared. So that fits into our one right here. So the top of this will then equal 1, because sine squared theta plus cosine squared theta equals 1. And on the bottom, we have cos squared theta. This is our reciprocal identity, where we have, so this is a reciprocal identity. This is a recip identity. And that reciprocal identity tells me that 1 over cos squared of x is actually equal to secant squared. So 1 over cos squared theta, cos squared x, will be equal to, our derivative will be equal to secant squared x. So this is one that I think you should add to your rules to live by. So our new rule to live by will be that if y equals sine x over cosine x, then the derivative of that will be equal to secant squared x. Let's take a look at some more. So let's take a look at the derivative for cotan of x, for secant of x, and cosecant of x. So let's start with cotan of x. So we know that if y equals cotan of x, using our quotient identity, if you remember, cotan of x, or cotan x, is equal to cos x over sine x. So we're going to use that now to rewrite this. So our cotan of x becomes y equals cos x over sine x. This we know how to take the derivative of. We can use our quotient rule to take the derivative of this. And remember, quotient rule, same as always. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. So we have my derivative of the top is sine x. Is negative sine x, sorry. Derivative of the top is negative sine x times the bottom, which is sine x, minus my top, which is cosine x, times the derivative of sine x, which is also cosine of x, all over the bottom squared, or sine squared x. Now we just need to simplify this using those Pythagorean identities again. So the one that we're looking at here now this time, we have y prime is equal to negative sine squared x minus cos squared x all over sine squared x. And the Pythagorean identity that we're looking at here is, again, our sine squared x plus our cos squared x is equal to 1. In this case, because they're both negative, we are going to say that that's equal to negative 1. So my derivative on top will be equal to negative 1 all over sine squared x. Now we're going to look at the reciprocal identity that tells me that 1 over sine x is equal to cosecant of x, or cosecant theta. And so we know if we have 1 over sine x, that will be equal to cosecant x. If I have negative 1 over sine squared x, that will give me a derivative of negative cosecant squared x. So the derivative of cotan is negative cosecant squared x. There's another one to add to your rules to live by. So let's look at the next one. So we have y equals secant x. We're going to use the reciprocal identity for this one, where we know that 1 over cos x is equal to secant x. We can always rewrite that 1 over cos x as cos x raised to the power of negative 1. So that gives us y equals cos x to the negative 1. Now we're simply going to use our chain rule. We're going to take the derivative of the outside times the inside, derivative of the inside. So we end up bringing the negative 1 down, negative 1 times what's on the inside. I'm going to reduce my power by 1, so that becomes to the power of negative 2, times the derivative of the inside. The derivative of cos x is negative sine x. So now we can simplify this. I'm going to rewrite this, this one back on the bottom. So we end up with negative sine x all over negative cos x squared. The negatives are going to cancel out, as you probably would expect. And so we end up with sine x over cos squared x. We know that sine x over cos x, we can break this down. We're going to break this down a little bit. So I'm going to erase that. Okay, erase that. So I want to break this down a little bit. So we have sine x over cos x, because what does this really mean? Sine x over cos squared x really is equal to sine x over cos x times 1 over cos x. Remember, we want to simplify it down so that we can try and eliminate everything that's on the bottom. That's our goal with all of this. So my sine x over cos x, we know is just equal to tan of x, and 1 over cos x is equal to secant x. So my derivative of secant x is tan x times secant x. Now let's look at the y equals cosecant x. Again, we're going to use our reciprocal rule that tells me that cosecant x is equal to 1 over sine x. So cosecant x is equal to 1 over sine x. And I'm going to write that as to the power of -1. So we're going to rewrite this as sine of x to the -1. Now we're going to go ahead and take the derivative of that using the same rule that we used before. We're going to use that chain rule, the same as we did last time. The -1 comes down, inside stays the same, reduce the power by 1, all times the derivative of the inside. The derivative of sine x is cos x. Now we're going to use our quotient identity and the reciprocal identity to break this down a little bit more. So I'm going to rewrite it as negative cos x all over sine squared x. And then I'm going to rewrite it one more time to split out that sine squared x on the bottom. So this is equal to negative cos x over sine x times our reciprocal. So this was my quotient identity, and this is going to be my reciprocal identity, 1 over sine x. Negative cos x over sine x is equal to negative cotan x, and this will be times 1 over sine x is equal to cosecant x. So our derivative for this, we could say, is equal to negative cotan x cosecant x. You always can reverse those around as well. It doesn't matter. Okay, so the 3 new rules that we've looked at for using the derivatives that we know how to take, sine and cosine, to determine derivatives of ones that we don't know. So cotan, secant, cosecant, and tan. These are 3 more rules that I'd like you to add to your rules to live by. So if f at x is equal to cotan x, then f prime at x is equal to negative cosecant squared x. If f at x is equal to secant x, then f prime at x is equal to secant x tan x, or tan x secant x. It doesn't matter what way you write that down. If f at x is equal to cosecant x, then f prime at x is equal to negative cosecant x cotan x, or reverse them around. It doesn't really matter. So I'd like you to pause the video right now and see if you can figure out the derivatives for each one of the following. And I apologize that B is scooched a little bit off the page, but it is just y equals secant 3x all squared. So pause the video, take a second to see if you can solve these using our new rules that we've just talked about, combined with some of our derivative rules, and then come back to check your answers. Okay, so let's look at our first one, A. Y equals 3 tan 2x. Remember that if I'm taking the derivative, I can, and I have a constant in front, the constant I can just multiply by whatever the derivative is. So this can be 3 times my derivative dy of dx of tan of 2x. And tan 2x just becomes the chain rule. So if we were to divide this out, saying tan of u and secant squared. So tan u becomes secant. My u is equal to 2x. That's the value that's in the brackets. And my derivative of that is just equal to 2. So using our chain rule and putting this all back together, we have the 3 in front times the derivative. So we have secant squared x 2x times 2. Now we can take this 2 and multiply it to the 3. So we end up with a derivative of 6 secant squared 2x. That's as far as we can go with that one. Okay, now let's look at the next one. This one is a power rule on the outside with the chain rule on the inside. So power rule on the outside, chain rule on the inside. And I think I'm going to dash over to another page just so we have a little bit more space to write this one out. Okay, so we have y equals secant 3x all raised to the power of 2. So like I said, we're going to use the power rule and we're going to use the chain rule for this. So power rule tells us that we bring the power down. So we end up with 2 times what's on the inside. We are going to reduce that power by 1. And then we are going to multiply all of that by the secant of 3x times my derivative, which is tan 3x, all times the derivative of the inside, which is 3. I've skipped a few steps there, but I'm hoping by now we kind of are understanding what our power rule and our chain rules mean. So now if we go ahead and simplify this, I can take this 3 and multiply it to the 2. So that gives me 6 in front. I have a secant 3x times a secant 3x. So that becomes secant squared 3x. And then I have my tan x. Whoops, I meant to say tan 3x there. I got looking at it, I'm like, that's not right. Tan of 3x. Like I lost a 3 there. Okay, so now let's look at the final one. So let's look at y equals 2 cosecant squared times x squared. So again, we've got, we know that when we take the derivative of something, a constant can stay out in front of the derivative. So we actually are just taking the derivative dy of dx of the cosecant squared x squared. And I'm going to do a little mathematical maneuvering here to move that square to the outside. So now we have the power rule and the chain rule again, very similar to what we had up top. So my derivative will be 2 times, we have, bring the power down, 2 times cosecant of x squared. The power drops to 1 times, now we've got our derivatives, so this is where we're going to use our chain rule, cosecant x squared. So we take the derivative of cosecant and multiply it by the derivative by itself and then by the derivative of x squared. So my derivative of cosecant is negative cotan, the x squared didn't go anywhere, times the original cosecant x squared times the derivative of what's inside here, which is 2x. So if we do a little bit of simplifying here, collecting of some like terms, doing some multiplication, I can multiply 2 times 2, that gives me 4 cosecant x squared times negative cosecant x squared times cotan x squared, all times 2x on the end. A further simplification of that leaves me with a derivative of, I can multiply this and this, so this leaves me with a derivative of negative 8x cosecant squared x squared, right? I've got my cosecant times my cosecant. We've brought the negative out in front, and then that's all times cotan x squared. Okay, I would suggest that you go and look at the handout that I've posted with this lesson for some homework questions and some practice questions. The answers are there. As always, if you have any questions, feel free to send me an email.